Hello everyone. First of all, congratulations on making it towards the end of this class. This is actually the very last lecture for this class in our Material and Energy Balance class. And we are going to be looking at psychrometric charts today. The text reading is from section 6.2. So we're going back a bit to sections chapter 6, where we're looking at Gibbs phase rule, and that's on page 282 to 284. The new material that we're going to cover for the most of this lecture is 8.4D, which is on page 432 to 439. So we're looking at this idea of psychrometric charts, which are cross plots of different intensive properties of two vapor mixtures. And the one that we're specifically going to look at is the most common one that we deal with a lot, which is air plus water vapor. So these are two vapor mixtures. This is a vapor mixture, and this psychrometric chart specifically is known as a humidity chart. But before we go into this humidity chart, I want to go back to section 6.2 and talk about the Gibbs phase rule to give us a background on why this chart actually works the way it does. So the Gibbs phase rule in chapter 6 talks about is this equation, which is the degree of freedom is 2 plus c minus pi. So let's go over each one of these variables. The df is the degrees of freedom. In this class, we have talked about degrees of freedom a lot, basically since the start and doing degrees of freedom for our material balance problems throughout this class. When we look at degrees of freedom, what we are talking about is how many variables do we need to fix, or how many variables do we need to specify before we can actually solve a problem. So in general, we talk about degree of freedom almost like a bad thing here, where we say we don't have enough information, how much more information that we need. But you can always look at it in a positive light where, for example, if you're designing a system, the number of degrees of freedom tells you how many variables you can play with for this system to actually work. So same thing down here in terms of the Gibbs phase rule. When we look at a phase diagram, the degree of freedom tells us the number of intensive variables that must be fixed or satisfied before we know exactly the state of that system. So analogous to the degree of freedom that we have talked about when we did our material balances. All right, the 2 down here in the Gibbs phase rule equation represents temperature and pressure. C here represents the number of components, and pi is the number of phases. So the Gibbs phase rule essentially tells us that based on the number of components we have in our mixture and the number of phases that we have that are coexisting, it can tell us how many degrees of freedom or how many variables we need to fix to know exactly the state of that system. All right, so let's do an example. Let's look at pure water again. And here's our single component phase diagram of water. Because we're looking at water only, so we only have one component, which means the C in our Gibbs phase rule is just 1. We're going to look at 3 different regions. So the first is in A, which is just in our liquid region. B is along the vapor-liquid equilibrium line, and C is at our triple point, and look at the degree of freedom value that we get from these 3 different regions. So let's start with A. In the liquid region, since it's all liquid, which means we only have one phase, so our pi is equals to 1. Put all the values that we know into here. 2 plus 1 minus 1, our degree of freedom is 2. This means that we need to specify 2 intensive properties for us to know exactly the state of that system. And by knowing the state of the system, we can know all other intensive variables. Looking at this phase diagram, we need to specify both the temperature and pressure to know exactly where we are at. For example, at point A, we can specify the temperature, but that's not alone is not enough to give us point A, because we can be anywhere along this line for it to exist as a liquid. So what we need to do is specify both the temperature and pressure before we can know the state of that system. And that's why we have a degree of freedom of 2 in that point A. Now looking at point B, we have a pi of 2 because now we have 2 phases coexisting. We have vapor coexisting with our liquid, where we have a saturated liquid and a saturated vapor. Putting that into our degree of freedom, we have a degree of freedom of 1, which means we only need to specify one intensive variable. We can specify temperature or pressure. We cannot specify both. For example, at point B, if we have specified the temperature, right away, because it is on the vapor-liquid equilibrium line, we know the pressure right away. We do not have to specify both the temperature and pressure. All right, so now looking at the triple point, now we have 3 phases coexisting. Both solid, liquid, and vapor are coexisting. Putting it to our degree of freedom, we have a degree of freedom of 0. There's nothing for us to specify. It is at a fixed temperature and pressure. We cannot specify anything for our triple point. So how does this relate to our psychrometric charts? The humidity chart can be found on page 432. So what I want you to do right now is turn to that page and look up figures 8.4-1 and 8.4-2. 8.4-1 gives the humidity chart in SI units. 8.4-2 is in English units. For the most part, I'm going to use 8.4-1 for all my examples and most of the homework examples as well. What a humidity chart is a cross plot of 7 intensive variables. And let's use the Gibbs phase rule to see why a humidity chart works the way it does. So we're going to look at the Gibbs phase rule. In this case, we have two different components, water vapor and dry air. So our C value is 2 in the Gibbs phase rule. We are only looking at the vapor phase, so we're looking at the air around us, right? So the water vapor and the dry air around us. So we are in the vapor phase, which means our pi is 1. If we put all that into our degree of freedom, the Gibbs phase rule, we see that we have a degree of freedom of 3. But for a humidity chart, we are essentially setting our pressure at 1 atmosphere, which makes sense because we are using this chart to design something that we will use around us. By setting our pressure at 1 atmosphere, this brings our degree of freedom down to 2. And why is 2 a nice number? Because you can use it to make into a 2D plot. So you can do it on a piece of paper. And what a degree of freedom of 2 means is that by knowing any 2 intensive properties, we can know the exact state of the system and we can know all other intensive properties. The humidity chart gives us 7 different intensive variables. By knowing any 2, we know where exactly we are on the plot, and we can figure out the remaining 5 that we have from that plot. So before we go on to actually look at the chart, one of the variables that we're going to look at is actually the enthalpy, the specific enthalpy of that stream. Because the specific enthalpy is related to both water vapor and dry air, we need to figure out what these values are based on. So what's the reference state used to generate these values? For the psychrometric chart, the reference states for water is liquid 0 degrees C and 1 atmosphere. For dry air, is obviously a vapor stream, is 0 degrees C and 1 atmosphere. So why is this important? Because we need to, if we choose to use other tools, for example, thermodynamic correlations or the tables, we need to make sure that the values that we end up using from those tools are with relation to these reference states, if we are going to use the enthalpy values from this plot itself. Let's look at the reference state for our steam table, so B5, B6, and B7. Recall that this was the triple point of water, 0.01 degrees C, 0.00611 bar, and it is the liquid state. Comparing this reference state from the steam tables in the reference state used in our psychrometric chart, you're going to see that we are at the same phase, we're almost at the same temperature, very close to the same temperature, and we know that the effect of pressure is a lot smaller than the effect of temperature. And many times, as an approximation, we just neglect the effect of pressure, which means that it is actually okay and it's a good approximation to use the steam tables in conjunction with the psychrometric charts, assuming that the reference states are close enough that we can use them concurrently. All right, so now let's look at the 7 different intensive variables. I've listed them down here for now, and we're going to go through the chart and see how we're going to read off each one of them. The first one we're going to see is a dry bulb temperature. A dry bulb temperature is essentially the temperature that we're used to talking about, the temperature you read from a thermometer. The second variable we're going to see is the moisture content or the absolute humidity. The third one we have is a relative humidity. We can also read off the dew point temperature, a humid volume, and like I mentioned, we have actually the enthalpy. But in terms of the enthalpy, we're going to read off 2 different things. First of all is the enthalpy of saturated air, and we're going to correct for that if it's non-saturated. And last of all, we have the wet bulb temperature. So let's go through each one of these variables and see how we can read off the plot. This is our 8.4-1. Let's start with our first variable, which is our dry bulb temperature, the temperature that we read from a simple thermometer that we have in the room. This is essentially what's on the x-axis. So right here you can see the dry bulb temperature. So that's easy, that's our x-axis. The second one we see is a moisture content or absolute humidity. We came across the concept of absolute humidity back in chapter 6, and we saw that the definition of absolute humidity is the mass of water vapor over the mass of dry air, and that is, in this case, on this plot, is on the y-axis right here, kilogram per kilogram of dry air. So that's our moisture content or absolute humidity. A quick note about this absolute humidity, because it is a ratio of the mass of water vapor and mass of dry air, we eventually, when we start to put this into our material balance problems, this is actually going to give us one specification or one relation, because it gives us the ratio of our masses. So if you're given a basis of dry air, right away with this moisture content or absolute humidity, we can know the mass of our water vapor as well. All right, so that's the x-axis and the y-axis. Let's look at the next one, which is our relative humidity. Relative humidity, the definition is the partial pressure of your water vapor over the vapor pressure at that particular temperature. And in this case, where you're going to see the relative humidity are these lines that go from the bottom left to the top right, and you can see here's 10%, 20%, 30%. And what you're going to see as you hit the left boundary right here, you have 90%, and the left boundary is your 100% humidity or your saturation curve. So that's the left boundary of this humidity chart right here. The next intensive variable we have is our dew point temperature, and this is the temperature at which the air would be saturated. So think back at the time when we looked at a single component phase diagram for water. We are in the superheated vapor region, and we are at a particular point. To figure out our dew point temperature, we'll move leftwards towards and hit the vapor-liquid equilibrium line, and that is our dew point temperature. The difference between the actual temperature and our dew point temperature is our degrees of superheat. So this is going to be very similar in the way that we're going to read our dew point temperature off of here. The scale where the dew point temperature is actually along the saturation curve. So here you can see the legend right here, and the scale is right here. You have 15 degrees, 20, 25, 30 right here. So that's the scale, and the temperature values are along this saturation curve. To find the dew point, just like we read across the phase diagram, you'll just move leftwards horizontally towards the saturation curve, and then you read off that scale along that saturation curve. Let's do a quick example. We have a relative humidity of 30% and a dry bulb temperature of 34 degrees C. So we are at a temperature of 34 degrees C right here, and we are at 30%. So if we move upwards towards the 30% relative humidity curve, that's where we are at. To read our absolute humidity, we just have to go right towards the y-axis, and we see that we have absolute humidity of 0.01 kilograms of water vapor per kilogram of dry air. To read the dew point temperature, we'll move leftwards towards the saturation curve. So from our point, we're just going to go horizontally across. We're going to hit right here, and you can see here's 10, and between each of the markings, we are actually at 14 degrees C. So that's our dew point temperature. We know our temperature is 34 degrees C, and the dew point temperature is 14 degrees C, so we can actually calculate our degrees of superheat to be 20 degrees C. All right, now let's move on to our next intensive variable, which is our humid volume. The definition of humid volume is the volume of 1 kilogram of dry air plus the volume of water vapor that's in that kilogram of dry air per kilogram of dry air. So what you're going to realize in the humidity chart is that all the variables are going to be given on a basis of per kilogram of dry air. And that's going to be important when we look at the enthalpy values and actually use it in our material balance calculations. So the units of humid volume would be meters cubed, so the volume occupied by the dry air and the water vapor per kilogram of dry air. And where you're going to see these values, these are the lines of negative slopes right here. You have 0.75, 0.80, 0.85, 0.90. So these are the lines of negative slopes that you can see that go across the humidity charts down here. So what happens if you're somewhere in between? You can see that the lines are spaced quite far apart. All you have to do is just interpolate or estimate between the lines. All right, so let's look at the sixth intensive variable, which is our enthalpy. Our enthalpy is going to be broken into two things. The first one is we're going to read the enthalpy of our saturated air. And then if we're not at saturation, there's going to be an enthalpy deviation that we'll read off of. So in terms of the enthalpy of saturated air, the scale we're going to read off of is this diagonal scale that's above the saturation curve. You can see the legend right there. So that's our scale. And the way we would read our enthalpy of saturated air is to just follow those diagonal lines depending on where we are at. Again, we have already mentioned this. When we talk about enthalpy, we have to make sure to remember what the reference state is. So the reference states used to generate this humidity chart is the water is at liquid 0 degrees C and 1 atmosphere. And for dry air, it is 0 degrees C and 1 atmosphere. So that is the enthalpy of the saturated air, but what happens if you're not at saturation, not at 100% humidity? That's when we have to look up an enthalpy deviation, and this will correct for our non-saturated air. Where are these values? These are the enthalpy deviations right here. You can see these lines, they are almost vertical, not exactly, but those are the lines. You can see here's a minus 1.2, minus 1.0, minus 0.8. As you get closer and closer to the left boundary, which is your saturation curve, the enthalpy deviation drops, and then once you're at the boundary, obviously there's no deviation, and so the correction is just 0. So these are the curves that are running almost vertical from the bottom to the top of the chart. The last variable that we have is known as a wet bulb temperature. So what's the difference between a wet bulb and a dry bulb temperature? Think about wrapping a thermometer or the bulb of the thermometer with a wet wick. And what happens is that because the wick is now wet, there's going to be evaporation that's going on, and the evaporation is going to cool the temperature down, which means your wet bulb temperature is going to be lower than your dry bulb temperature. If you already have 100% humidity, what happens is that there's no evaporation that can go on because your air is saturated with water vapor. You cannot evaporate any more water, which means there's no cooling effect. Your wet bulb temperature is going to be the same as your dry bulb temperature, and it's also going to be the same as your saturation dew point temperature. So it has the same scale as your dew point. So we're going to read off the exact same scale as the saturation curve. You can see that down here it also says wet bulb temperature. The only difference is now instead of going horizontally to read your dew point temperature, we're going to go diagonally following those enthalpy lines to read our wet bulb temperature. And like I mentioned, if we are at the saturation point, so our relative humidity is 100%, the dew point temperature is the same as our wet bulb temperature, and it's going to be the same as our dry bulb temperature. All right, so those are our 7 intensive variables. Let's do a quick example. In this case, we have a relative humidity of 10%, dry bulb temperature of 50 degrees C. What I want you to do is go ahead now and pause the video, figure out where we are on this chart, and then read off the other 5 intensive variables. Once you're done with that, restart this video and check your values. Okay, I can just continue, right?
Yep.
Okay. All right, welcome back. Hopefully you figure out, at least give this a shot and figure out the other 5 intensive variables. So let's go through and check this. We are at a relative humidity of 10% and a temperature of 50. So we are right here in terms of our point. So let's read off the remaining 5. I've been giving you the values right here. In terms of the absolute humidity, you read straight across to the y-axis, so it's about 0.0076 kilograms per kilogram of dry air. The dew point temperature, you go the other way horizontally until you get to the saturation curve, and you can see that it is about 10 degrees C. In terms of the wet bulb, you're reading off that same scale along the saturation curve, except now you're going to follow the diagonal lines. So down here, I'm going to draw a parallel line that's diagonal, parallel to those diagonal lines, and I'm going to end up right here. You can see that this is 20, 21, 22, 23. This is 24, so I'm somewhere between 23 and 24, so that's 23.6 degrees C. In terms of the humid volume, those are those lines of negative slope. We are right here, so we are between this line and this line. This is 0.90, this is 0.95. We are almost kind of in between, just kind of eyeball where we are at, so we are in between that. So we have 0.925 meters cubed per kilogram of dry air. The last one we have is our specific enthalpy. We have 2 things we need to read. First of all, we need to read the enthalpy at saturation, and we need to read the enthalpy deviation. Enthalpy at saturation is the exact same thing like we read the wet bulb, except now we're going to keep going until we hit that the scale of the enthalpy at saturation. So in this case, you can see if you read off, it's about 71. That's the enthalpy at saturation. We are not saturated, which means we need to figure out the correction. In terms of the correction, look back at our point. We are right here. Our enthalpy deviation here is minus 1.0. Here is minus 1.2, so we're somewhere in between that, so I call it minus 1.1. You have 71, minus 1.1, our correction, and so we have 69.9. So again, the 71 comes from the enthalpy at saturation, the 1.1 comes from the enthalpy deviation, and that's how we end up with the enthalpy of this stream that is of relative humidity 10% and temperature 50 degrees C. So this is an example of how we can use the chart with any 2 known intensive variables. We can read the other 5. There is an additional example that's posted with the lecture handout. That's question 8.82. I'm not going to go through in this video, but go ahead and try that question and double check your answers with the answer that's posted with the lecture handout. But before I end this lecture, what I want to do is, can we show this 69.9 kilojoules per kilogram of dry air using the tools that we had before? So using our thermodynamic correlations and using our steam tables. Can we show this exact same enthalpy value? Note that down here, the enthalpy of this stream is the enthalpy of the combination of both your water vapor and your dry air. And in this case, the basis is given per kilogram of dry air. So before we, to actually use our prior tools, let's just pick a basis. We're going to pick a basis of 1 kilogram of dry air. So the mass of dry air is 1 kilogram. We know the absolute humidity. We just read it off from the psychrometric chart. And so we saw that the absolute humidity was 0.0076 kilograms per kilogram of dry air, which means from here, we know we have 1 kilogram of dry air. Our mass of water vapor is 0.0076 kilograms. So the enthalpy of this stream is just the mass of dry air multiplied by the specific enthalpy of dry air plus the mass of water vapor multiplied by the specific enthalpy of water vapor. We can now use prior tools that we know to figure out this. We're going to use our steam tables to calculate the specific enthalpy of water vapor. We're going to use our thermodynamic correlation to figure out the specific enthalpy of our dry air. Noting that we already have a reference state, we have to use the same reference states that was used in the psychrometric chart. So for our dry air, recall that in the psychrometric chart, it was 0 degrees C and 1 atmosphere. So we are going from 0 degrees C to 50 degrees C, which is where we are at, and we want to figure out what the enthalpy of dry air is. Look up the thermodynamic correlations. In this case, it's just the integral of Cp dt from 0 degrees C to 50 degrees C. Look up the A, B, C, and D values, do the integration, and you end up with 1.542 kilojoules per mole. We want everything in terms of kilojoules per kilogram, so now we can convert that by using our molecular weight of dry air, which is 29 kilograms per kilomole, and we have 50.07 kilojoules per kilogram. Now we can look up the specific enthalpy of our water vapor using our steam tables. So again, we are just going from our reference state, which is liquid and 0 degrees C. We're going to ignore the pressure because the effect of pressure is small. Going to vapor at 50 degrees C, we can read up using our table B5 by just neglecting the temperature. In this case, you'll see that this is 0. The other way to look at it is we have already mentioned that we can use both the psychrometric charts and the steam tables together because their reference states are about the same, which means this reference state from the steam tables is essentially 0 as well. So looking that up, we have 2592.2 kilojoules per kilogram. Put all of that back into our enthalpy equation, and we see that multiplying those enthalpy values by our mass, we have a specific enthalpy of 69.8 kilojoules. This is, if we want it per kilogram of dry air, we divide by the mass of dry air. In this case, we pick 1 kilogram. And we end up with 69.8 kilojoules per kilogram, which is very similar to our 69.9 kilojoules per kilogram of dry air. So this is just a way to check to make sure that we can get the same values using the reference state as stated in the psychrometric chart to get this same enthalpy value. That's all I have for this that's all I have for this lecture. We will have 2 more examples with material balances and looking at how we can use these enthalpy values into our energy balance. So go through those video examples, work hard, be smart. I'll see you then.